In this unit, we're going to be studying acids and bases and using the knowledge that we acquired from the equilibrium unit to better understand what happens during an acid-base reaction. But in order to study acids and bases in more detail, we need a fundamental understanding of what exactly acids and bases are. So the most fundamental definition of an acid or a base that you should be familiar with is the Arrhenius definition of an acid and a base. So an Arrhenius acid is actually one that increases the concentration of hydrogen ions when it's dissolved in water. So the traditional HCl, HBr, you have a hydrogen that's going to be produced when you dissolve it into solution. An Arrhenius base is a substance that increases the concentration of hydroxide ions when it's dissolved in water. What you should notice, though, is this definition limits you to aqueous solution. So you have to have hydroxide produced by the base and hydrogen ions produced by the acid, which limits you, as you'll see in a little bit. What I want you to do right now is I want you to use your textbook in order to complete the table that I provided, identifying specific characteristics of acids and bases. So pause this video right now, and then we'll continue on. All right, the next definition of acids and bases is a little bit more inclusive, and that's the Bronsted-Lowry definition. A Bronsted-Lowry acid is defined as a substance that donates a proton, while a Bronsted-Lowry base is one that accepts a proton. And so the acronym that I use to remember that is BAD. Bases accept, acids donate, BAAD. So let's look at some examples to see how these Bronsted-Lowry acids and Bronsted-Lowry bases actually work in a reaction. So if you look here, I give you a reaction. Hydrochloric acid is reacting with hydroxide ions to produce water and Cl. So the first thing that we need to do is identify the Bronsted-Lowry acid and the Bronsted-Lowry base. If you notice HCl, if you compare HCl to the chloride ion on the product side, HCl has lost that proton, the hydrogen ion. Therefore, it is going to be the Bronsted-Lowry acid. Hydroxide has accepted that proton, that hydrogen ion. Therefore, OH is your base. Keep in mind, I'm going to be using the term proton synonymously with the term hydrogen ion, because remember, if you have a hydrogen ion, the only thing that's left is a single proton. Now, there are two new terms that I need to introduce, and it's the concept of conjugate acids and conjugate bases. So every acid has a conjugate base, and every base has a conjugate acid. So for hydrochloric acid, because it's an acid, it functions as a Bronsted-Lowry acid. That means that Cl minus, the chloride ion, is its conjugate base, while for hydroxide, water is its conjugate acid. So water is the conjugate acid in this case, and chloride is the conjugate base. In this lesson, we're going to apply what we've recently just learned about acids and bases, and we're going to apply it to the concept of equilibrium. In the first part of this lesson, I'm going to talk about the autoionization of water, but in order to understand what the autoionization of water is, I've got to go over two specific terms, amphoteric and amphiprotic. Now, water is amphoteric and it's amphiprotic. So what exactly does that mean? Well, amphoteric means that a substance can act either as a base or an acid. And amphiprotic means that a substance can accept or donate a proton. Water can act as either a base or an acid, and it does so by either accepting or donating a proton. Well, what does that look like? Well, water, as we saw in previous reactions, can either act as an acid or a base, or if it's reacting with itself, one water molecule can act as a base and the other one can act as an acid. And this reaction is called autoionization because you're producing ions, but water is doing it to itself. So if you look, the water on the far left-hand side, that donates a proton to the water next to it, which serves as a base because it accepts the proton. And so what you produce as a result is a hydroxide ion and a hydronium ion. Now, water mostly exists as the molecule H2O and not as these ions. And that's why water does not conduct electricity, because the majority of water exists as a molecule and not as ions. If it didn't, if in fact the right-hand side of this equilibrium were favored, then pure water would be able to conduct electricity, but it doesn't. So the water that you drink for the most part is just H2O, although there are a couple of ions in there. it's not significant enough to change the physical properties of water. All right, so we're going to take this concept of the autoionization of water, specifically this reaction, this equilibrium reaction, and we're going to come up with a new equilibrium constant, and specifically that equilibrium constant is called the ion product constant. And the ion product constant is Kw instead of Kc or Kp. It's Kw, and that equals, notice, just as a review from equilibrium, you do products over reactants. Well, your products are hydroxide and hydronium, so you've got those concentrations. The reason why we exclude water, liquid water, is because it's a pure substance. And so hydronium ion, the concentration of the hydronium ion times the concentration of the hydroxide ion, those multiplied by each other, that gives you 1.0 times 10 to the negative 14th. Because remember, as long as we're at constant temperature, your equilibrium constant doesn't change. Now, this value is extremely important as we prepare to be calculating pH and pOH, as you'll see in just one second. So just as a review, if your concentration of hydrogen ions is higher than the concentration of hydroxide ions, that means you have an acidic solution. Keep in mind, hydronium and hydrogen ions, we're going to be using them interchangeably. If the concentration of hydrogen ions and hydroxide ions is the same, then you have a neutral solution. And finally, if the concentration of hydroxide is higher than the concentration of hydrogen ions, then you're going to have a basic solution. Notice for all of these that your ion product constant, your Kw, is still 1.0 times 10 to the negative 14th, no matter what's happened to your concentration of hydrogen ions or hydroxide ions. So looking at this example here, it's asking us to calculate the concentration of hydroxide ions. We know the concentration of hydrogen ions. Therefore, we can use this formula, your ion product formula, and then just plug in the values. I know that my Kw is 1.0 times 10 to the negative 14th. I know that the concentration of H plus is 5.6 times 10 to the negative 6 molar, and so I'm just calculating for my concentration of hydroxide ions, and I find that it's 1.8 times 10 to the negative 9th molar. So the second part of this question asks you to indicate if the solution is acidic, basic, or neutral. Well, since 1.8 times 10 to the negative 9th is a lower concentration than 5.6 times 10 to the negative 6, that means that my solution is going to be acidic because I have a higher concentration of hydrogen ions than hydroxide ions. Let's now actually look at pH. You might have looked at this concept in a previous chemistry class or even in middle school, but we're going to look at it in quite a bit more detail now and learn how to calculate it based on concentrations of hydroxide ions and hydrogen ions. Keep in mind, thinking back or looking back at your notes, concentration of hydrogen ions is extremely low, and so what we've created to make these values more manageable is this pH scale. And so the pH simply equals the negative log of the concentration of hydrogen ions. So if you notice here, while a solution is acidic if its concentration of hydrogen ions is larger than 1.0 times 10 to the negative 7th, meaning it's going to be a higher concentration of hydrogen ions than hydroxide ions, your pH has to be less than 7 for it to be considered acidic. Similarly, if it's neutral, if your solution is neutral, then the pH is going to be equal to 7.00. And if it's basic, while the concentration of hydrogen ions is less than 1.0 times 10 to the negative 7th for it to be basic, the pH is going to be larger than 7.00. Just like pH equals the negative log of the concentration of hydrogen ions, the pOH equals the negative log of the concentration of hydroxide ions. And if you do a little bit of manipulation, what you can realize is that pH plus pOH, that actually equals 14.00. And I got that by finding the log of your Kw, of your ion product constant. So pH plus pOH equals 14.00. That makes it really easy to convert between pH and pOH, as you'll see in just one sec. So in this example problem, I'm given my concentration of hydrogen ions. It's 5.6 times 10 to the negative 5th. And so the first thing that I'm going to solve for is my pH. And all I need to do for that is to take the negative log of my concentration of hydrogen ions. And so when I do that, I get 4.25. Now notice Hydrogen ions, there's 2 sig figs for that concentration, while for pH there are 3. And so here's one of the exceptions to the rules as far as significant figures are concerned. However many significant figures your concentration has, that equals the number of decimal places your pH or your pOH will have. And so I rounded this to 4.25. Now the next thing that I'm going to calculate is my pOH, because I know that pH plus pOH equals 14. So I'm going to take 14, subtract 4.25 from that, and I get 9.75. Now keep in mind your pOH equals the negative log of your concentration of hydroxide ions. Remember, there's an implied base 10 for your log. And so to solve for your concentration of OH, I'm going to take 10 and I'm going to raise it to the negative 9.75. Now, if you are still unclear about logs and how to calculate your concentration of OH or H plus from pH or pOH, you need to look up how to solve logs or come in and see me. Okay, so all you're going to do is take 10, raise it to the negative 9.75. And keep in mind, because there are 2 decimal places, I want 2 significant figures for my concentration, so I got 1.8 times 10 to the negative 10th. Now, the last thing this is asking you is this acidic or is it basic? Well, the way that I do it, I look at my pH, and I remember if my pH is less than 7, it's going to be acidic. If it's greater than 7, then it's going to be basic. So since your pH is 4.25, my solution is acidic.